right. Wow, this is amazing. So many people here. It's like a sea of people all the way to the back. So I think we're about to get started. So this good? Okay, all right. Well, good morning, everyone. So today there's a tremendous focus on advancing, graphics, performance, monetization, just getting the game shipped. And oftentimes behaviors, which we think is probably the most critical piece of a game, is sort of often overlooked. My name is Jeff. I'm in the machine learning team here at Unity. So today I want to talk to you a little bit what we're thinking about how we actually help you create behaviors in your games with some of the things that we're doing with different studios. So first, what do I mean by behaviors? So you have the single, non-player character or player character. You have squads of player characters or non-player characters. You also have things like the actual story itself, the narration, even the player assistant, and actual game objects themselves. So all of these pieces together actually create what, when a gamer plays the game, the actual behaviors. So when we talk about, the different levels of behaviors, there's actually, several different levels. So we talk about strategy and tactics, which are revised, sort of every 30 minutes. So you have a squad of NPCs, they have to take over a base. Oops. You have the navigation. So you have an individual NPC that has to sort of figure out how to jump, get through around a wall, and all these different actions. And you actually have the animation itself as a behavior. So if you think about, your body has all these joints. How does the actual, player pick up the gun and actually just sort of walk around the levels? And so when you think about it, if you're starting from the top to starting from the bottom, if you think about it at the top, it's very highly combinatorial, meaning there's a lot of discrete options. So, I could take a taxi, I can drive myself, I can go to the airport, I can fly to Seoul, I could take a shuttle, and so forth. As you get further down, it sort of becomes what we call like a continuous nonlinear problem. So think about your joints. Your body has 50 different joints, and joints can be moved, there's so many different ways our bodies can move. And so really it becomes a very continuous problem as you get sort of, below on the different kinds of behaviors. Now there's actually a lot of different solutions when we talk about behaviors in the game. There's coding, which is, you have your C# scripting, a lot of state machines, and this is probably something most game developers are very familiar with. You actually have what we call like solvers as well. This is sort of your navigation modules. You sort of like, find the shortest path. And this is really designing the problem, and then you have, the AI sort of solve the problem for you. And then you have my personal favorite, which is the learn, this is the machine learning approach. And there are a lot of new things that we can talk about today. So as you go from coding all the way to learn, you think about the behaviors become sort of controllable and then all the way to autonomous. So you're coding a lot, it's very controllable. Using machines to control the behavior, it becomes more autonomous. So kind of going back to today's approach, when we talk to game developers, this is sort of the approach today. Code, code, code. When you're doing animation, you're doing a strategy, you're doing a navigation, it's just a lot of coding. But we find that it's actually a really, really difficult approach, especially if you have games that have a lot of different kinds of behaviors, a lot of interactions. So what we think, there's actually a different sort of way to solve different problems in the behavior, and that's what I want to talk to you guys about today. We have a couple of products and projects with our Unity Labs team, as well as the ML Agents Toolkit and our Inference engine. So I'll talk a little about these in sort of the next sections. So there's a Unity Labs AI Planner. So some of you may have heard of this. This was announced at Unite in 2018 in Austin. And it just went into preview. It's actually a preview package you can get in 2019.1, and it was launched after GDC this March. So the way I can actually describe how does this AI planner work? If you think about search, so search is a pretty, everyone knows how search works. You have a maze, and you want to get to, into the maze in the shortest path, or you want to get to the end of the level in the shortest way. So when you set up search for navigation, you sort of set up the problem this way. You sort of define it as a graph. So you're at this location, it costs you 10 to go to this location, another 9 to go around this location, and eventually you can kind of map out how you get to the goal. So most navigation systems today use something like A*. So once you can define the search as sort of this way, you can use something like A* algorithms to sort of find the shortest path. You didn't write any code, you actually just set up the problem this way. So what is the AI planner? It's actually the same approach. You're actually setting up the behavior as a search tree. So for example, I'm at my house. I'm at the start point. I have a key to my house. I have a high level fatigue. In the AI planner, you actually can define your states pretty richly. I travel to my home. Okay, I'm gonna get a little bit tired. Okay, I'm at home now. And then I get in my home. I don't actually have to travel anywhere. I walk inside my home, and then I use the key. So now the key is gone. Maybe I take a nap. Now I feel really refreshed, and I can get to my goal. So same thing. You sort of define all the possible states in your game, and you use the algorithm to solve what's the best behavior you're trying to drive. Now in this case, it's trying to get to the goal without dying. So the algorithm actually finds these certain paths, and it's the same problem that you would use for search. And that's exactly what the AI planner really is. You define all these states, and we include some algorithms to help you find this. There's no coding. You're just setting up the problem, and you're letting the search algorithms sort of pick the best paths. So just a quick high level on the architecture for the AI planner. You have a planner. So this is the thing that actually does the searching. You have a controller that actually controls the game. So this kind of queries the planner. It kind of embeds it back into the game and kind of understands the state and actions of the game. And you have this what we call the planning domain. So this is a really, really key component. This is actually how you define the states in your game. So let me just show you a little bit of an example. So you have something called eat. When you eat, you have an eater, and you have some food. And these are sort of the traits of these different objects. And you can also apply these traits to other game objects. So there's an apple, it's food. Banana, it's food. It's the same thing. It's the same traits. They're just different game objects. And then when you define them, you can actually set up what we call these flexible variables. So at runtime, you can declare these. For example, the eater has a hunger of 9.5. The apple has food. And they have to be, when you eat something, you have to be in the same location. So if I have, for example, food at the end of the table, I have to actually be together to eat it. So when you define these things, this is actually what happens. So if you can actually define eat in this way, that's sort of generic and with these certain kinds of variables. And then there's the actions that you have to define. So in this case, you eat, you have to have a who, and you kind of have to have a what. There's also some preconditions that you need to satisfy. The agent has to be an eater. The object has to be food. They have to be in the same location. And then the effects is okay, you eat the apple, now I'm less hungry, and then the apple is gone forever in the game. And these can all be instantiated at runtime, so you don't have to write a bunch of subclasses for this to work. You can use the planning domain to sort of scope out the game this way. So really, this is kind of how the AI planner works in a nutshell. You sort of design the problems instead of a solution. The AI solves the problem for you, and you can actually do this in runtime. You don't have to define a lot of subclasses. And then you sort of do what we call intelligent domain modeling to compensate for the runtime execution. So some of the features of the AI planner, we include what we call the child-based heuristic tree search algorithm. So just pretty common search that we apply to here. It works pretty well, but the team's also incorporating new ways to solve the plan. You can plan under uncertainty, so actions can have multiple effects with different kinds of probabilities. So it doesn't always have to be find the shortest path or find the goal. It can be all these other different ways. And of course, it uses the latest optimization using DOTS, data-oriented technology stack from Unity. So this is the AI planner. Again, check it out. I'll kind of leave this up here for a second. It's in preview. You can get it as a package. There's a sample project on GitHub. A lot of discussion forums, and of course, you can always contact our AI research team for a little bit more. So this is really the solver, and this is how one of our solutions that we think is really going to be impactful for a certain class of games. Now I want to talk a little bit, which is a little bit my sort of favorite areas on the machine learning side. So now that we have a way to sort of solve games from this perspective, we can use something like machine learning to solve lower parts of the game. So we have the machine learning agents toolkit, and we have the Unity Inference engine. The two things that we've been working on for the last year or so and working with different game studios. So before I start with that, so there's been a lot of advances in machine learning and gaming. And you see some of the top companies in the world in AI research are actually trying to solve these. So you have OpenAI solving Dota 2, and you have companies like DeepMind solving StarCraft 2 and Go, which is one of the hardest games to solve from a machine learning perspective. And so with all these advancements, we're really not coding these machines anymore. We're actually teaching the machines how to play these games. And from this, we find that there's a lot of very interesting applications from a game development perspective. So before we kind of get in, what are agents? Okay, so agents perform actions in their environments. At any given moment, the environment is in a certain state. From the states, the agents collect observations, and from the observations, actions are taken according to their policy. Now, this policy is extremely key point. And so the whole reason you do this, you want to create a policy for how the agents behave in the game. So just kind of a quick illustration. So you have a policy, you have some observation. So I know the location, I know how fast I'm running, I know the rotation, I can see stuff in the camera, I have a lot of bullets and the enemy's somewhere in front of me. Based on the policy, I can take a certain action. I can move, I can jump, I can turn, I can shoot, and I just kind of repeat this frame by frame. So how do you actually create these agents, and how do you actually create the policy? So I want to introduce what we call the Machine Learning Agents Toolkit. It's an open source toolkit used for training intelligent agents using deep learning. So how can you really use ML agents in a game? Well, one we call from the player agent. So you can actually have a machine actually play the game from the point of view of the player. So this could be used for game testing, game balancing. You can also create non-player agents. And so this could be the enemy or a companion. And this is actually something you could try to put into a game as like a non-player character. And the last is what we call the invisible agent. This is actually where the agent is the game itself. So the agent can change the scene, it can change different objects in the game, and really it's around this notion of dynamic content generation, difficulty tuning, and just really creating a different kind of engagement for player. So there's sort of just 3 ways you can actually apply agents using a machine learning agent in a game. So how do I actually put this in a game? So you have this policy. So one of the biggest challenges is hey, I like neural networks, I like deep learning, how do I put this back in the game? So our team has actually created what we call the Unity Inference engine. So you can run any ML agents model on the CPU or on the GPU on any platform that's supported by Unity. So we have a couple examples we'll show you. One is on a phone, and also using some of our stress testing. So here's sort of the workflow. You have ML agents plus inference. You integrate into the game, you train, and then you sort of embed this back into the game. So let me talk a little bit about integrate. So this is just kind of the high-level classes that we include as part of the ML Agents Toolkit. Now, in your game, you can extend these classes that actually specific to your game. So starting from the top, we have an agent, and this is what actually controls the game object itself. You have a brain, which are connected to agents, and the brain contains the policy. And you have the academy, which is what actually controls the game itself and actually interfaces between Python and other training systems. So all this is included inside the ML Agents Toolkit. So different ways to set up. You can have one brain controlling a bunch of different agents. Okay, so same agent, these are all little puppies controlled by one brain. You can have what we call multiple brains. So you can have some puppies, some weird-looking cats, I think these are little mice. So you can have different brains doing different things with different policies for different kinds of agents. So really 2 ways. You can just do single agent, or you can also do multi-agent. So that's everything you set up in the game. Now you actually have to train these agents. So this is actually where the fun really begins. So ML agents, and actually in the area of gaming research, there's actually 2 sort of ways that we think that are applicable to train these games. So starting with reinforcement learning, the agents learn through experience. And I'll show a quick demo of kind of how that works. A lot of a trial and error until it becomes optimal. The simulation could be sped up greatly, so you can change time scale to 4x, 10x, how you want. And then you sort of get this superhuman ability in the agent. And so let me show you what that really means. This should be playing. So this is like a very, very typical sort of chicken crossing the road game. I think it's like a chicken or it's like a Pikachu. I don't really exactly know. But as you can see, it's hasn't done any training. It's just sort of taking some random actions. Doesn't really quite know how to play the game. So after about an hour, it starts to figure out, okay, don't get hit by a car, pick up the presents, but it's still not that great. It still, hits the cars and all these things. Getting a little bit better, getting a little bit better. Still getting there. Okay, so after 6 hours, so now it can actually play the game. It's just running through this game like no other. So you can see it knows how to play, it can see things. I mean, literally frame by frame, it knows what decision to make. So this is just a really, really simple example of reinforcement learning. You set up the game, and then you can basically train your agents to play the game at the most optimal way possible. So the second way we want to talk a little bit about is what we call imitation learning. So these agents learn through demonstrations, and I'll show a video about how that kind of works. It mimics the behavior quickly, so you play the game, and the machine sort of picks up how to play. And then we recorded these demonstrations, and then you sort of get this human-like player. So that should play. So this was the demo we showed last year with our friends at CyberWalrus, who it's called Antigravity. So you have a human on the left side and a machine on the right. So it's about 5 seconds in. The machine really hasn't really figured out how to play the game. So about maybe around 15 seconds, the machine really starts to understand. So you see it's starting to kind of learn how to turn. So after about 25 seconds, as you can see, the machine actually learned how to play this racer game just watching the human play. So this is, again, a very simple example to illustrate imitation learning. All right, and so after this is just fully trained, as you can see, the machine plays really well, almost exactly like the human. So there's a lot more in here. So I just talked about reinforcement learning, imitation learning. There's a whole lot of concepts about deep learning, deep reinforcement learning, behavioral cloning that we actually include in the toolkit. We support the OpenAI Gym interface. We support Google Dopamine. We can allow you to train on the cloud. All of this included in the toolkit. All of it open source. You can go right now and check it out, and let us know how it works for you. So with that, there's actually an embed component. So we integrated our game, we trained it. Now we got to actually put it back into the game. This is actually where a lot of like difficulties happen when you try to ship a production game. So before that, so after you do training, you get this brain, all right? So in this brain has a policy. And the policy is what actually controls the agent. So that's really what happens after training. You really get this brain that can control the agent. So really what's actually under the hood of this brain? So what is it really? It's actually a neural network. So if you're familiar with neural networks, it's something in this case, it's in 100,000 of parameters. These parameters could be pixels on a screen, it could be states, it could be any kinds of observations. And when you execute a neural network model, it has to have these massive, large matrix operations. And then in the case of some of these examples, you may be controlling multiple agents. So why is this really hard to embed in a game? One, just the sample brain that we saw today uses something around 26 matrix operations. This is every time it needs to make a decision. Your game also needs to run graphics, it needs to run physics, and you have all these other systems in the game that you're competing for the same amount of resources. And of course, you have to maintain FPS minimums, you have hardware support, and all this stuff really just adds up to, hey, this is kind of cool, but it's really hard to put into a game. So I want to introduce the work that our labs team is doing around what we call the Unity Inference engine. It's high performance, uses the C++ backend scripting, the burst compiler, and also the compute shaders. We have this generic platform agnostic API, so you train in one platform, and you could deploy to any other platform. Is GPU and CPU inference supported? So sometimes you have a very small neural network where a CPU can run it very easily. Sometimes you need to use the GPU, like if you have a lot of visual observation. So also supported for both modes. Optimized for different platforms. So when you run a neural network on a mobile device versus a desktop device, the underlying hardware changes. So we do a lot of partnerships. Because we're Unity, we have partnerships with Microsoft, Apple. So we actually work with Microsoft with DirectML, which is one of their machine learning frameworks for Windows devices. And also like CoreML, which is Apple's machine learning toolkit for Apple devices. So you just use this engine, and it kind of just takes care of all the optimizations below. And for my favorite, it's fully integrated with ML agents. So if you use ML agents, you can use this out of the box today. I just want to kind of comment on this. So today, we only support a small set of use cases. But if you think about AR, you think about VR, you think about games, the more and more machine learning you put in the games, the more and more support you're going to have to need for different platforms. AR is a great example. A lot of object detection that it's really hard to do just out of the box. So we want to support every platform that Unity supports, and that's sort of our goal. So just do a quick demo. This is Puppo. He's our sort of mascot. And the demo I'm going to show is all completely controlled by ML agents and the ML agent's brain. So let's just show this quick. Okay. So this is actually running on a phone device, but we just sort of show the video because a lot of difficulties sometimes with that. So as you can see, as you're putting more dogs in there, each of these dogs has its own, it's controlled by a certain policy. But as you add more dogs, you see the inference is only taking about 1 millisecond, and you're still maintaining about 50-ish so frames per second. Now, in a few weeks, Microsoft is going to publish a new benchmark in their DirectML, where they're actually going to run 1,000 of these dogs on a Windows, using DirectML, and they're going to publish a lot of the performance statistics. They're using Puppos because they just need some sort of data set to benchmark their inference performance. So just kind of one thing is that's the aim, is you do have to sort of have some sort of level of performance as well in inference. So that's kind of the workflow. We integrate, we train, and we embed. That's really, it's a pretty simple workflow. Also want to talk a little bit about Jam City. And so one of the things that, this isn't just like a research project that we do in a lab where, we're just making some cool stuff, but no one actually is trying this in the game development. We actually partner a lot with Jam City, and they give us access to their games, and specifically Snoopy Pop. So Snoopy Pop's a bubble shooter. I don't know if you guys, this game is fairly common. You got a bubble, you're gonna shoot it, and you try to get the bubbles to come down. So what we did was actually incorporate ML agents. So we integrated ML agents. We set up all the observations. So this is actually, if you can see, it's a low fidelity version of what the machine sees. And then we define the actions and all the rewards. And so we actually integrated ML agents. We actually trained it to see how far we can. Now, Snoopy Pop has over 1,000 levels. So that's kind of our benchmark. How many levels can our machine get up to? So I just want to show a quick video. I think this will load. So this is actually after about 2 hours of training. So this is just one level. So you can see the machine's kind of going through it. And so, and then it kind of continues on the level. So a couple of things. There's the machine learning component, but then also how do you put this into a game? So there's all the trickiness with both things. Like actually putting it into the game is actually more difficult than the training side because your game has a lot of other code, has a lot of other systems. This game had Facebook integrations that you had to kind of deal with. But it's just one of the things that we weren't trying to bring this more into the gaming side. So that's it, my presentation. I also have, I think, some opportunity to answer some questions. So again, we're trying to kind of sit at the intersection of different solutions for behaviors. And today I just wanted to kind of illustrate a few things that we're working on. And of course, this is all the stuff, you can go get ML agents, you can contact us, you can email me, you can find me on Twitter. We post a lot of our updates that are on blog on Twitter, and there's several of our engineers you can follow. I'm on the second floor today. If you guys want to see some demos, you want to look at some of the code, just come on upstairs. Also, our good friend Yakashik, he has a session tomorrow on the research side of ML agents, which we didn't talk a lot about today on research, all the new algorithms, all the cool AI stuff. So he'll talk a little bit tomorrow about the cooler, well, to my side, some of the cooler stuff in what's the new research in the machine learning side. So with that, I will happy to take some questions. I think I'm supposed to get an iPad. And again, I think I only have about 10 or 15 minutes for questions. So if you have any questions, come upstairs, second floor. We'll be there all day. Oh, no questions? Oh, okay. All right, sounds good. Well, actually, no questions. So with that the case, then thank you again for your time. I'll be up here for about 10 or 15 minutes. If you have any questions, feel free, come chat. But thank you so much.